Okay. If the change in M1V1 is equal and opposite to the change in M2V2, and hopefully we're pretty well conversant with how that follows from Newton's third law. Okay? Then we could write that out as M1V1F minus M1V1I equals M2V2I minus M2V2F. Okay? Where I've applied the negative sign all in one step. This would be M2V2F minus M2V2I, but the negative sign then makes it M2V2I minus M2V2F, right? Have you done momentum in your dynamics? Okay, well, the formula everybody grabs onto here and totally bypasses the whole idea of impulse momentum, thereby relegating themselves to inability to solve a problem that does rely on impulse momentum, is the formula we're going to get here. We look at what we have before. We can M1V1F plus M2V2F equals M1V1I plus M2V2I. Okay? In other words, we got a negative M2V2F here that can come over with this one, right? And we have a negative M1V1I that can come over here, and it's obvious. Now, often this will be expressed in one of many ways. It could be M1V1 plus M2V2 equals M1V1 prime plus M2V2 prime. Just one notation where the prime doesn't indicate a derivative, it indicates after the collision. Okay? Now, since that's confusing to have a prime on there that you might confuse with a derivative, although if you use it and understand the context, it's often written like using two different letters for before and after. So you'd have M1V1 plus M2V2 equals M1U1 plus M2U2, where U is your velocity, generally considered after the collision. Okay? It's very simple to do that. Okay, this is totally equivalent to the impulse momentum theorem. You can get the impulse momentum theorem from this, you can get this from the impulse momentum theorem. Or at least this result of the impulse momentum theorem. Okay? Does that make sense? Again, now that's an equation people grab. It makes a lot of intuitive sense. It just says your total momentum doesn't change. So this says and then we put the thing that I haven't mentioned with all this today in an isolated system. Okay? Because, of course, if your system isn't isolated, as in the lab last time, this is not true. And hopefully you work that out for today. Convince yourself that impulse momentum can't, that those velocities that you got do not confirm the impulse momentum theorem. They don't contradict it because you do have external forces, force of the ramp on especially the first ball due to the spin, okay? And I wanted to try to correct for that today, but we'll get that in lab next week, because by then you'll really understand why it should be, okay? Hopefully you already do. Okay, so there are going to be some problems. I haven't selected them yet, but I do have the document. So I'll pull about maybe as many as a dozen problems out. Some of them are really simple, like an elephant has mass 3,000 kilograms and it's running at 7.5 meters per second. What's its momentum? Well, actually, I didn't even include that problem. Multiply mass times velocity, that's the momentum, right? And we've already done that implicitly. We understand how to multiply mass times velocity. We should understand that that's momentum. I'll also recommend that you read the chapter in your book. Okay?
Chapter 8?
I believe so. You don't have to worry about some of the stuff later in the chapter, like rocket propulsion and stuff where they do the thing I was talking about, where the delta of mv is m delta v plus v times delta m. It's just a product rule, and it's true for the same reasons. But we haven't talked about that yet, and we'll do that next week to kind of wrap this up, okay?